Have come to the distribution track, and first talk is investigating the scalability limits of distributed Erlang. More scalability here, and
I'm talking about the scalability of distributed Erlang. I'm from Glasgow University and working in release projects. First, I talk about release project, why we have done this research and what release project aims to achieve. Then I talk about DBMS. It's a benchmarking tool that we developed for benchmarking purposes of Erlang. And finally, we see the results and in terms of global operation, data size, and computation time, server processes like Gothenburg, server, and finally, conclusion and future. This project is a bootcamp project which aims to scale Erlang, a large core, many core. So there are 8 partners in this project. Glasgow University is coordinating this project. Internally is coordinating. Why Erlang? Why we have chosen Erlang for this project? Because of the successful commercial application in Erlang, and also its feature like shell locking concurrency, asynchronous message passing, and process completion transparency, and many other features that makes Erlang portable. In this project, we are working in different levels. Some people are working to scale in virtual machine, language level, infrastructure level, and profiling and refactoring. In language level, this research that I'm talking today is in a scalable computation model or a scalable distributed Erlang. For a scaling distributed Erlang, we first need to identify the problem or bottleneck. And we needed a benchmarking tools for this. Doing some benchmarking, and for doing some benchmarking, we need a scalable benchmarking application that can be run on hundreds of nodes and thousands of code. And there wasn't such a tool requirement, so we developed our own tool. We call it DBMS. It stands for Distributed Erlang Benchmark, and it's based on Bench. Bench is an open source benchmarking tool for Riak, NoSQL videos. For scalability purposes, DBMS has a P2P design, which means there is no specific role for a specific node. All nodes have the same responsibility and behave independently. There is no coordination, synchronization, and no single point of failure. So it's reliable because if any of the nodes crash, the benchmark is continue to work. Here we see. First, I want to show how the cluster works in this benchmark. Then we go inside each DBMS, that how DBMS works from internal view. From the outside view, we have a physical host. This physical host can have multiple Erlang VM. Each Erlang VM host will run one DBMS instance. So, it's fully connected because all nodes, regardless of whether they are on the same host or not. Inside the DBMS, what's happening inside the DBMS? A supervisor process runs a number of worker processes. Each worker process selects a command randomly from a list of commands. This command are spawn, RPC, every distributed Erlang command. a node that's the command should be run on that node. It's run the command on the node, and the result is back and collected on the node. And the result latency throughput failure are recorded in CSV file. We have a supervision tree for reliability and fault tolerance. There is 8 core on each. I will talk about the cluster and the specification of each node. But we have 8 core on each node, so we choose 40 worker process on each node to keep it relatively busy. CSV files also are located local to avoid any this contention, access contention or less fault latency. In the bench, we have some category of command. Some command are P2P command or point-to-point command. The command that have a source and destination. Source run a command on destination. Destination run it for y microseconds. So the result is back. Again, x byte is sent, x byte is received. The latency is calculated here. We have the other category of command, our local command, that just one node is run that command and there is no communication between nodes. And global command means that all nodes in cluster get involved. And the result gets ready when all nodes successfully configured. P2P command that we have now in bench, and this will change in future. Spawn, which asynchronously call a function at a remote node. RPC synchronously do that, and server process, we use here the synchronous call of server process, gen server and FSM server process. As here is shown, here the process is doing what a computation, and the result is back to the source. For a spawn, this process should be created and then die, but for RPC and gen server process, this process exists and then remain there. For local command, we use register name, unregister name, varies, and global varies. Global varies is belong to global module, but it's a local operation because there is no communication. It's read just from a local table. And register and unregister are associating a name with a process because of reliability purposes. We need this function. Global function we use is register name and unregister name. Globally associate a name with period. They are globally, it means when we register a name, all table and all VM in cluster should get updated. A worker process, I showed worker process on inside the DBMS. A worker process has internal state to avoid an exception that if the process be registered 2 times with 2 different names, it raises an exception. So to try that exception, we are following this state. When we register a name, we call varies, and then we register that name to be possible to be able to register a name. We run this benchmark on Calcul cluster at Uppsala University. Calcul cluster has 348 nodes and 2,000 core, 8 core per each node. The memory RAM and operating system and the Erlang version R16 has been used in all our experiments. This benchmark, we run this benchmark on 10, 20, 30, until 100 nodes, cluster of nodes to see the effect. Our experiment run for 5 minutes. We have one Erlang VM per each house. And as always, we have one DBMS instance on each VM. CSV file are aggregating at the end of the benchmark. For example, we have 70 nodes. 70 CSV files are aggregated to find the total throughput, total failure, and latency. First, we see global command benchmarking. In this benchmark, we want to use global command. We use spawn and RPC, global command, and local. We use all kind of command. RPC and spawn are run with 10 byte argument size and 10 microsecond computation time on the remote node. Global command are register and unregister, and varies also is used. As we see here, as we use more global command, the scalability become more limited. Here, there is no, you see here the number of nodes until 100 nodes, and that one is through the number of successful operations during 5 minutes benchmark. As we increase the number of global operations, the scalability become more limited. It's clear that global operations are a problem, but to make sure we see here the latency of all command here. We see that the other just register and unregister commands, the latency are increasing dramatically. For example, here for 100 node cluster, just registering the name takes 20 seconds. So, but the other commands are very low. In terms of data size, here we don't use any more global operation or commands. We use just spawn and RPC, which are P2P commands, and we keep constant the computation time, 10 microseconds. We increase the data size from 10 to 10 kilobytes per unit. Here we see the effect that data size has on scalability, and it doesn't mean that it doesn't scale, because in compare with this, the other size, this one. But if we show that in a single diagram, you see that this one also is stable. Maybe this part not. Data size in this benchmark, because accessing the nodes more than 100 nodes on Calculate cluster, it's time consuming. But we could run this benchmark up to 150 nodes. And in this benchmark, we use 1 kilobyte argument size and 1000 microsecond or millisecond. We see that distributed Erlang scales linearly. And until 150 nodes, we have 1,200 cores. But it doesn't mean that RPC and spawn scale the same. When we see the latency of each of these commands individually, we see that a spawn RPC, the latency of RPC grows as the cluster size increases. And the question is that why RPC in comparison with a spawn doesn't scale there? It's not a big problem because it's a scale, the latency on 100 nodes is not huge, but in comparison with spawn, it doesn't scale. For understanding why RPC is a problem or a bit problem, we need to know how RPC works. For each on each node, on each VM, Erlang VM, there is a Rex gen server process which is responsible for handling RPC. And this process is shared between, it's not just used by our application, it's used by whole VM. Other modules of VM are also using this process. So this process can be overloaded as a shared service. So the reason that the latency of RPC increase could be the single process which is responsible for handling all RPC content. Our experience with Riak 1.1 shows that there is some server process that become overloaded and make Riak scalability. Riak scalability is around 6.0. I'm saying Riak 1.1. We don't know about the improvement that has been made on the next version. So the question is that how server processes like Gen server or FSM server are scalable. Do they have a problem, or that's for a specific reason? In this benchmark, we are using Gen server and FSM beside Spawn and RPC. It includes all these point-to-point command. We run it with 10 byte argument size and 1 microsecond, and the same for Gen server and Gen. And we see that as we use more server process, the scalability improves. This one belongs to where we just use 1% of server process call, and this one belongs to when all calls are server process. When we see the latency of each command, again we see that RPC solved the risk that doesn't scale well, but the other server processes even are better than Spawn. So we can see that server processes are not problem if they be used properly, not becoming overloaded. Even they are better than Spawn, because maybe a Spawn is creating the process, but for server processes, the process exists. We need to create a new process.
So I didn't understand that. What's the difference between Gen server and Rex? Or do you have many Gen servers?
Rex is a single process on Erlang VM.
Yeah.
So it's.
And how many calls do you receive?
How many?
How many calls does it receive in this test?
We see the total number of throughput. For example, here we have 1 billion operation. So if we divide it, for example, in this case, that is 50-50. If we divide it between server processes, we can.
Is all nodes communicating with all other nodes?
Yes.
And in the Gen server case, you have more than one Gen server?
No, one server. One Gen server on each.
That receives as many calls?
Yes.
As Rex?
As Rex. But Rex is shared. Rex is not all Gen server. Rex is a Gen server that is used by VM, one other part of VM.
But what is it doing then? That makes it so big difference.
Sorry?
What is Rex doing that makes it so slow compared to your own Gen server?
I think because it's,
receives as many calls from your application.
I think because Rex is not just used by my application. Rex is used by other parts of Erlang OTP.
Yes, I understand that. I just was curious what other parts are shown in this test that makes such a big difference.
I don't know, because Rex, maybe someone should search OTP and see where Rex is used and for which purposes it's used, and it's need more investigation to see that which part, because it's a big library and nobody can tell easily that Rex is used for 20 times and this place and for these purposes. It's something.
Yeah, I would have profiled it if I got those results.
In terms of that, how many modules and use it? Oh, yes, more investigation can be done to find that. Okay, we demonstrate that global operations are bottleneck for scalability of distributed Erlang. We plan, or we have done, we improved the implementation of global operation by grouping nodes. We introduced S groups and grouping nodes in distributed Erlang, and it's another session. Can talk about it. Our result also shows that RPC call, latency of RPC call raised as cluster size grows. So we suggest that as much as possible, avoid using RPC for the scalability purposes. A spawn, if you can replace it with a spawn, do that. Several processes scaled well, and they show the lowest latency among all P2P commands. And also, we are also benchmarking other benchmarking application, and we plan to run it on a larger architecture. We plan to run it on Blue Gene until the end of the project. So the future work is still our working on.
Can you go back to the slide where you show the difference between global performing poorly? Go back a few more. It's like, forward to the register, unregister call slide. One more. Forward again.
This one is global.
The one where you show the difference between unregistered and registered. I guess it doesn't matter. I guess a critique I have of the benchmarking against global, it seems that it seems that's not a criticism of distributed Erlang. That's a criticism of the synchronization required for making the global call, right? So I think by benchmarking, you're just blocking on those operations waiting to complete. And it's not necessarily showing that there is a problem versus the non-existence of a problem. So like in Riak, we would avoid to use global because it requires synchronization. But that doesn't mean that other messages that might be being sent by distributed Erlang to maintain its own state aren't necessarily a problem. So I'm confused. I guess I'm confused as to what that slide is really showing other than time waiting to synchronize. But maybe I'm misunderstanding it.
I think the problem is synchronization between all nodes. And when we use it loud, that's the reason. Because they say, here you see that the latency dramatically increased. So
yeah, I guess the criticism is the calls to global register aren't necessarily an implementation detail of how distributed Erlang is maintaining its own state. That's a application level decision. Not all the time, but for a majority of times, you could avoid an application that needs to make a lot of those calls and still experience a problem with distributed Erlang because of some other internal state tracking mechanism it needs to keep the network working.
Yes, I think global operations are not used frequently or in a large amount in typical distributed Erlang.
So I think it'd be interesting to perform a benchmark that tried to be representative of, maybe this would be interesting, I don't know, but to try to be representative of this, how much synchronization distributed Erlang needs itself to maintain its own state versus things that it can do loosely synchronized. But yeah, I don't know. I don't know how it's implemented.
But
So
I think this one is important. This one shows that if you don't use global operation, distributed Erlang, which is 150 nodes, are fully connected, scalable. And this latency shows that, and also this latency shows that, except RPC, which we discussed for the problem, the other one, the latency doesn't increase.
yeah, okay. So you're saying that our problem with the RPC is that it requires serialization at one gen server. Yeah, I get. Yeah, okay. Yeah, it's very interesting to. Yeah, so I don't know. I'm thinking about it in terms of Riak, and there are other things about the way that the TCP connections are handled that concern us, as opposed to mechanisms like RPC that we try to avoid at all costs because we realize that you pay a huge penalty there. That's why if you look at Riak, I think we have 5 RPC calls, 3 of which are like 6, and they're in applications that we're hoping to, like sub-applications that we're hoping to not be there anymore, but, like, especially RPC multi-call, but things like that. So yeah, I don't know.
But I'm interested in this, personally, I'm interested in this latest because it shows that the cluster size doesn't affect the latency.
Sure, yeah, no, I totally understand that.
That's
Yeah.
something that, yes?
A comment about the Riak 1.1.1.
Yes.
So it had the same single Erlang process bottleneck that the Rex server does. It's just that the bottleneck process was a single supervisor process that was being used for each of the queries being handled by Riak. And so once we got rid of using the supervisor for tracking many worker processes and moved to another mechanism, then that particular bottleneck in that slide disappears.
Yes.
So that was the paper last year. That was the poster at least last year.
We
which
showed that in the paper that in the next release, yes, it's improved.
Yeah, it's side job, right? Yeah.
Okay, I think we have to stop there. Thanks again.